Good morning, friends. We shall be discussing a very interesting chapter named Special Theory of Relativity. Special Theory of Relativity is one of the greatest discoveries of this 19th century. All the Nobel Prizes later on, about 10-20 Nobel Prizes, have gone on the study of this special theory of relativity. And you all know the most disastrous and most useful atomic energy has come up because of this study of theory of relativity. Let us now start, and let me divide this chapter into following topics. We shall be discussing what is relativity, then we shall discuss what is classical relativity, then we will be coming to the origin of theory of relativity due to Albert Einstein. Interestingly, this theory is so great that Nobel Prize is a small thing for it, and I may mention that there was a meeting of Nobel laureates to commemorate this great discovery by awarding the scientist of the century for Albert Einstein. Okay, that is another story. Let us see what is relativity. In daily life, we come across many terms just like big, small, large, less, more, and so on and so forth. These are relative terms. We see there are two lines. This is a bigger line, this is a smaller line. Now, bigger and small, that is relative. This is bigger than this. Suppose I draw a bigger line, that this line becomes smaller than this. This is relative. So, the length with respect to another length is a relative length. However, if we speak that there is a length of 30 centimeter, that is absolute length. Similarly, there are many quantities, or rather I may say there are almost all quantities which are relative. The absolute quantities are only a few, countable few rather. The starting of theory of relativity comes from Newton and Galilean mechanics. Newton said that length, mass, and time interval are absolute quantities. They are not subjected to any relative motion. Subsequently, Galileo forecasted the theory of classical relativity. Accordingly, if some physical quantity is observed at some place by some observer, and the same quantity is observed by another place by another observer, then how do they look like? This is what we call the relative observation. To discuss the theory, we need few important parameters. For example, frame of reference. Frame of reference is any rigid structure with respect to which we measure motion. For example, a tree, a road across a tree. So, the tree may form our vertical z axis, and two perpendicular roads may form x and y axis. Thus, tree is a good frame of reference. Temple is a good frame of reference. But a goat cannot be a frame of reference. That will clear how the frame of reference is selected. The frame of reference, I take two frame of references, one is moving with respect to other with constant velocity. Velocity means constant speed in a fixed direction. Then such frames are known as inertial frames. Inertial frames. In these frames, obviously the laws of inertia, F is equal to ma, force is equal to mass into acceleration, holds good. Such frames are known as inertial frames. The frames which are accelerated, they are non-inertial frames. The relativity that deals with inertial frames is special theory of relativity. And the relativity which deals with non-inertial frame is general theory of relativity. Our domain in present discussions is special theory of relativity. Then there is an event. Event may be any physical happening. For example, blasting a cracker or emitting a light pulse by an LED or glowing a bulb, or these are events. Events means physical happening. To discuss the relativity, classical relativity, Galileo obtained the transformations. What are the transformations? Transformations are the equations interrelating the physical quantity observed in one frame of reference with the quantity observed in another frame of reference. That means the equation connecting the two observations are known as frame of reference. Let us consider two frames of references. One is a S frame of reference, another is a S dash frame of reference. And we consider that S dash is moving with respect to S with velocity v. We select our x-axis in the direction of motion of the frame, and therefore we have these axes. Suppose we have got a point, any point here P. The position coordinates of point P with respect to S, I write as x, y, z at any time t. And the position coordinates observed by observer in S dash, I name as x dash, y dash, z dash and t dash. So what are transformations? Transformations are the equations which relate x, y, z, t to x dash, y, z dash, z dash and t dash. According to classical relativity or Galilean transformations, suppose at t equal to 0, both the frames were coincident at say O. That means O dash was at O at t equal to 0. Therefore, in time t, S dash has moved a distance Vt, and therefore we can write x dash as simply x minus Vt. There is no motion along y, so y dash is equal to y, and similarly z dash is equal to z, and according to Newton, length, mass and time interval are absolute, therefore t dash is equal to t. These are the Galilean transformation equations. If I differentiate this with respect to t, I will obtain velocity transformations, and subsequently I can multiply it by m to have momentum transformation and so on and so forth. So these are the Galilean transformations, and this represent the classical relativity. There is a problem now with this classical relativity. Where is the problem? When we discuss electromagnetism with respect to classical relativity, according to classical relativity, a frame moving with constant velocity and a frame at rest are identical, as determined by this equation F is equal to ma. Both the frames are identical, whether the frame is moving with constant velocity and the frame at rest. Let us see how does this concept is compatible with electromagnetism. We consider an observer here O stationed, and there is a charge put at a point O dash. There is a charge Q. Now when O is at rest, repeat, when O is at rest, it observes only electric field E, determined by Coulomb's law. However, when observer O moves with respect to O dash with velocity v, constant velocity v, then with respect to O, charge is moving with velocity minus v, and therefore the moving charge will constitute current, and therefore a moving observer will not only observe electric field, he will observe electric field as well as magnetic field. So we see that the rest observations of an observer at rest and the observation of an observer moving with constant velocity are different. That means classical relativity is not compatible with electromagnetism. Therefore, there was a very simple task how to go ahead with these observations. This tempted Albert Einstein to forecast a new theory of relativity which may be compatible for both the mechanics as well as electrodynamics. And this is basically the origin of a special theory of relativity. Coming back to the classical relativity, it was observed that since motion is always relative, therefore, we should have such a frame which is absolutely at rest. If we can select such a frame which is absolutely at rest, then all the motions with respect to that absolute frame can be easily forecasted. Now, that to determine an absolute frame of reference, Michelson and Morley designed an experiment, and they thought that ether forecasted, the concept of ether forecasted by Fizeau and Foucault may be used an absolute frame of reference. What they percepted is that ether is at rest, and therefore, when light is moving through ether, the observation of light with respect to ether will represent absolute motion. Therefore, they took Michelson's interferometer, which we discuss in interference experiment, and oriented one arm of Michelson's interferometer in the direction of motion, and another arm was perpendicular to the direction of motion. We just say this is Michelson's interferometer, okay? Then velocity v. Earth is moving with velocity v with respect to stationary ether. And therefore, light traveling in the direction of the Earth's motion will have velocity c plus v, and the light traveling against this will have a velocity c minus v. Whereas the velocity of light traveling perpendicular will have this path, and this velocity obviously in this direction will be c square minus v square square root. See that time taken by light in traveling in x direction is, if distance is d, this distance is also d, then d upon c plus v plus d upon c minus v. Whereas the time taken, this is I can call as tx, and time taken for light traveling in y direction, transverse direction, will be 2d upon under root c square minus v square. You can easily see that the two velocities, two times are not the same. Since the two times are not the same, there will be a time difference, and this time difference will result in a net path difference. And therefore, if we consider the speed of Earth with respect to ether, then there will be a shift in the fringes. But how to observe the shift in the fringes? The answer to this came up. They rotated the instrument by 90 degrees so that y comes in the direction of Earth's motion, and therefore the time difference which were existing earlier will be doubled, and corresponding to that there will be a shift in the fringes. Gentlemen, the instrument was made so precise that it could measure a fringe shift of 0.002 fringes. The expected shift was of the order of 0.1 fringe, and therefore instrument was 100 times more sensitive than what is to be measured. There were enormous attempts made to observe the shift in the fringes, but no fringe shift was ever observed. That means the result of Michelson-Morley experiment was negative. This experiment yielded two important results. Number one, absolute frame of reference is impossible, because we failed to observe ether as an absolute frame of reference. The second conclusion which supported or which came from this is that light is not subjected to relative motion. That means whatever observations they write, C plus V, C minus V, this is not possible for light. And that was the starting point that supported Albert Einstein. So the two things taken together, that electromagnetism is not supported by classical relativity, and second, Michelson-Morley experiment result of Michelson-Morley experiment was negative. This is the starting point of the theory of relativity. To understand the theory of relativity, let me consider a very simple experiment that will give the essence of the theory of relativity. Let us consider a man on a trolley or a jeep, and there is a tree. On this tree, a bird is sitting. The man wants to fire a gun to kill this bird. The trolley is at rest. He fires the bullet with velocity v. The bird, of course, flies, and we have a detector here to detect the speed of the bullet. Obviously, the bullet of the speed will be detected by this detector to be v. Now suppose this trolley is moving with velocity v. Then we can easily see that now the velocity of the bullet detected will be v plus v, because trolley is moving with velocity v and bullet is moving with respect to capital V with respect to the trolley. Therefore, with respect to the earth, tree is located on the earth, the speed becomes v plus v. To see whether the bird has been killed or not, the gentleman lights a light. Light travels with the speed c. So according to Galilean transformations, the speed of bullet recorded should be c plus v, but the measurement suggests that it is c. That means classical relativity is not applicable in case of light. From this experiment, we draw two conclusions, very important conclusions. Number one, the result of an observation not only depends on where from it is observed, that means motion is relative, and second, it also depends on what is observed, because the observations for a material particle are different from the observations for light. That means the behavior of light is altogether different from the behavior of material particle motion. And that is the starting point of relativity. Now, let me come directly to the postulates of special theory of relativity made by Albert Einstein. See, relativity is very simple. What these two postulates speak, let me brief you first, then we will analyze them. The first postulate is known as law of physical equivalence. Law of physical equivalence. Physical equivalence. This law speaks that the laws of physics remain the same in all inertial frames of references. That means physics will remain universal for whatever be the observer. Of course, the observer should be an inertial observer, because we are dealing with spatial theory of relativity. The physical laws remain the same in all inertial frames of references. Inertial frame of references. What do you mean by physical laws remain the same in all the inertial frames of references? That means the equation expressing a physical law retains the same form. The same form. For example, if in S frame we observe F is equal to ma, then in S dash frame we will observe F dash m dash a dash. That means remaining the same form. In technical words, we speak the physical laws remain invariant. Physical laws remain invariant. This is the first postulate of the theory of relativity. The second postulate establishes that speed of light in vacuum is a universal constant. It is not subjected to any relative motion. I mean, speed of light, what he has spoken, speed of light means velocity is a vector quantity which varies with direction, but speed does not vary with direction, and therefore the speed of light remains the same. It neither depends on the nature of the observers nor it depends on direction. Direction independent, and therefore velocity of light is a scalar quantity. It is not a vector quantity. The speed of light remains the same. It does not depend on motion of the observer and the direction of motion of the light. This can be understood in terms of electromagnetic theory, because the speed of light is under root mu 0 epsilon 0 and vacuum. Both are mu 0 and epsilon 0 are universal constants, and therefore this postulate is easily understood nowadays. But think at that time when Einstein predicted that the speed of light is universal, there were more than 130 experiments to find out whether this postulate is correct or not. They measured the speed of light to the greatest accuracy, and they found that speed of light remains the same. So these are the two postulates. Enumerating the postulates of the special theory of relativity, let us now start examining the consequence of these postulates. To find out consequence of these postulates, we have to find the transformations as per the postulates of the theory of relativity. Lorentz, with the help of Albert Einstein, deduced the relativistic transformations. These are known as Lorentz transformations. What are the essential requirements that these transformations should observe? There are two observations. Number one, the transformations must be linear. Why the transformations must be linear? The law of physical equivalence, corresponding to one event in S, there must be one event in S dash. That requires the transformation to be linear. This is in accordance with the the first postulate of relativity. Second, under the condition velocity less than c, this is called classical limit. Lorentz transformations should go to Galilean transformations. These are Galilean transformations. GT, Galilean transformations. So under a small velocity limit, v less than c, Lorentz transformation should go to Galilean transformation or should reduce to Galilean transformations. The transformation should be simple because the theory of relativity is quite simple. It speaks natural observations, or you can say it speaks the observations of nature. Nothing very complicated is observed. If these transformations obtained by simple considerations do not suffice, then we will go to complicated transformations. But the first step should be the transformation should be very simple. If we follow these three conditions that Lorentz transformation should observe, an obvious guess will be that the transformations will be of this type: x minus vt alpha, y dash is equal to y, z dash is equal to z, but we cannot speak about t. We shall observe under relativity what does t dash is equal to t. Let us see whether it holds or not. The condition is that alpha should not depend on x or t. Why? Because if it depends either on x or on t, the transformations become non-linear. That violates this first condition. Therefore, it should not depend on x and t. However, it should depend on v. Otherwise, how shall we incorporate motion? So, alpha should be independent of x and t, but it depends on v. Let us find out whether t is equal to t dash or not. To see this, let us observe the first postulate. As per physical equivalence, s dash moving with velocity v with respect to s is physically equivalent to s moving with velocity minus v with respect to s dash. So, if s is moving with respect to s dash with velocity minus v, we can write the transformation like this: x must be equal to alpha x dash plus v t dash. This follows from the law of physical equivalence. This follows from the law of physical equivalence because these are equal. So, I substitute the value of x dash from this equation onto this equation. Let us see what happens. Alpha x dash I write as x minus vt plus vt dash. Solving this, alpha square x minus alpha square vt plus alpha vt dash. This gives me t dash is equal to 1 minus alpha square upon alpha x upon v plus alpha t. So, we see that in general t is not equal to t dash. T will be equal to t dash T will be equal to T dash when alpha is equal to 1. That means if alpha is equal to 1, it goes to Galilean transformations, which is not possible. And therefore, T is not equal to T dash. See that a biggest pillar of Newtonian mechanics, that time is absolute, has proven to be wrong. So here is a failure of classical mechanics. One aspect, it is a failure of classical mechanics. Now, to find out the transformations, we have to find the value of alpha. Because we have got a value of x dash, we have got a value of t dash, y dash is equal to y, and z dash is equal to z. If we can find the value of alpha, we can find the value, we can find the transformations or coordinate transformations. Now see how to find alpha. We have used the first postulate only. We have got another postulate, second postulate, and we can use second postulate, that is speed of light is universal. It remains the same onto relative motion as well as it remains the same in all the directions. To consider second postulate, what we do, let us see that a light pulse is emitted and it is observed by both the frames S and S dash. The light pulse will expand and it will travel in all the directions with the same speed. Therefore, the light disturbance will expand on the circumference of a sphere, not only for S but also for S dash. The radius of this sphere will be x dash is equal to ct dash in S dash and x will be equal to ct in S. That is the observation. So these two equations can now be used here. How? Let us see here. I multiply this equation by C, entire equation, this equation, time equation I multiply by C. So Ct dash is equal to 1 minus alpha square upon alpha. X is obviously Ct and I have multiplied by C, so it will become C square T upon V plus alpha T. Ct dash is obviously x dash. Ct dash is obviously x dash and x dash is alpha x minus Vt. I substitute the value further, alpha x is just Ct minus Vt. So the final equation is alpha Ct minus Vt is equal to 1 minus alpha square upon alpha C square T upon V plus alpha T. See, alpha, this T is common everywhere and therefore T cancels out. And if we solve it further, it is very simple to obtain that alpha will come out to be 1 minus 1 upon square 1 upon square root of 1 minus V square by C square. And therefore, we have the transformations. Okay, let us find out what does these Lorentz transformations give us. Let us examine the two other pillars of classical relativity, namely the length and time. To discuss or to arrive at, let us consider that a rod is located and we associate it a frame S dash with the rod. That means in S dash the rod is at rest. The definition of length is the distance between 2 points. That is called length. And therefore, the rod of the length as observed by S dash is x2 dash minus x1 dash. And since the rod is at rest in S dash frame, it is the proper length or an accurate length. The length at rest. This is the proper length. the length observed by S is the length of a moving rod, because S dash is moving with respect to S with velocity v, and therefore x2 minus x1 is the relative length. What we do to have a precise result, both x2 and x1 are measured simultaneously through a laser beam. Similarly, x2 dash and x1 dash are measured at the same time using a laser beam, and therefore now we can find out from Lorentz transformation how does x2 dash minus x1 dash means L0 and x2 minus x1 L are related. So substituting the value x2 dash minus x1 dash equal to x2 minus Vt, because they are measured simultaneously, I am using T, not T2, under root 1 minus V square by C square minus x1 minus Vt upon under root 1 minus V square by C square. And therefore, what do I have? x2 minus x1 upon under root 1 minus V square by C square. That means L upon under root 1 minus V square by C square. This simply gives me L is equal to L0 under root 1 minus V square by C square. Since this factor 1 minus LB square by C square is less than 1, therefore moving length appears to be contracted. That means the length which is in motion is always smaller than the length which is at rest. That means length at rest is the maximum length. The second important aspect is under V less than C, V less than C, L is equal to L0. That means we have a classical result. We have a classical result. We can depict this variation graphically also by letting L upon L0. This is V by C, and you see that the variation becomes important only when V is comparable to C. The variation in length will be effective or to be considered only when V is comparable to C. The length contraction has another important aspect. At V equal to C, the length reduces to 0, because the material cannot disappear altogether, and therefore speed of light is unachievable for physical objects. No physical object can move with a speed, the speed of light. That means speed of light is highest achievable velocity for the material particle. Let us now come to time dilation or relativity of time. To consider relativity of time, we have to take two identical clocks and consider one of the clocks to be moving. If we consider a mechanical clock or two identical mechanical clocks, then length contraction will feature up and our observations may be erratic. Therefore, we consider two biological clocks. Where are the biological clocks? We consider twins, a brother and a sister. Twins, so their hearts are identical. We consider one of them, say brother, moving in a rocket, which is moving with a very high speed relative to the earth, and sister is located in the laboratory. The observation or heartbeats are observed through remote electrocardiogram, and the interval between heartbeats is taken as the time interval. Now let us see how these two time intervals, that means heartbeats of brother moving frame and sister at rest frame, are related. Since S dash is a moving frame, and therefore the proper time will be the time of the sister. That is, the time observed by S will be a proper time, and therefore we take reverse Lorentz transformations. That means reverse Lorentz transformation means we relate the quantities observed in S dash to S. That means reverse Lorentz transformations we will replace prime quantities with unprime quantities, unprime quantities with prime quantities, and velocity by minus v. That means x will be equal to x dash plus vt dash upon a square root of 1 minus v square by c square. Y will be equal to y dash, z will be equal to z dash, and t will be equal to t dash plus vx dash by c under root 1 minus v square by c square. C square, sorry. These are reverse Lorentz transformations. Then let us come to the point we observe T2 minus T1 will be called T0, and T2 minus T1, T2 dash minus T1 dash will be the improper time interval. This will be proper time interval, these two pulses here and these two pulses here. This is of the one who is in the laboratory and the one who is in the rocket. To find out the relation, we substitute the value of T1 and T2 from here, corresponding values. C, this is T2 minus T1 will be equal to, again, we take the observation at the same place, x dash. That means, while measuring the heartbeat, the brother or sister are not allowed to displace themselves, and therefore T2 will be equal to T2 dash plus Vx dash by c square upon under root 1 minus v square by c square minus T1 dash plus Vx dash by c square upon under root 1 minus v square by c square. This gives me T2 dash minus T1 dash upon under root 1 minus v square by c square. This relation can be written as T is equal to T0 under root 1 minus v square by c square. What does this physically represent? The time interval of moving clock is dilated. Dilated means the clock runs slow. That is, moving clock runs the fastest, and the clock which is in motion becomes slow. That means there will be slower aging effect in a moving clock and faster aging effect in a clock at rest. You can obviously think, when relativistically brother and sisters are moving, they are twins, they should have the same age, but relativistically, if one is observed to be moving in a rocket and another is stationary in the laboratory, their age will be different. Obviously, this is theory of relativity, which is sometimes misunderstood by many. Gentlemen, if the relativistically age is growing up, so will there be a biological changes with the age? The answer is no, because all the biological changes are with respect to the proper frame, and therefore aging effects will not feature up. Now let us examine, or let us see whether there are experiments to prove theory of relativity. The answer is yes. There is a profound experiment to prove time dilation and length contraction. The experiment is like this. Pi mesons are produced in an accelerator, synchrocyclotron, and they decay to mu meson with a half-life of 1.8 into 10 raised to the power minus 8 seconds. And they travel with a speed of 0.99 c. The experiment is like this. In a laboratory, there was a tunnel and two detectors were located, D1 and D2, at a distance of 30 meters. Obviously, a flux of particles were injected here. The flux were observed N0 here and N here. Because this is radioactive decay, the particles will decay through this relation. N upon N0 is equal to 1 by 2 raised to the power T by T. This will be the decay flux. Now, since they have to travel a 30-meter distance, the time taken by the particles, pions, to travel through 30-meter distance will be 30 divided by almost 3 into 10 raised to the power 8. That means 10 into 10 raised to the power minus 8 seconds. That means T upon T comes out to be 10 into 10 raised to the power 8 divided by 1.8 into 10 raised to the power 8. This is approximately 5.7, and therefore the flux of the particles expected will be 1 by 2 raised to the power 5.7. This is 0.02. That means 2% only. The experiment detected that there were 60% flux at the time of exit. This is quite large and not within the experimental error. This can be understood with the help of theory of relativity. How? Because meson is a fast moving frame, therefore its time will get dilated. Moving clock runs slow. So what will be the relativistic time? T half dash will be 1.8 into 10 raised to the power minus 8 divided by 1 minus v square by c square. 1.8 into 10 raised to the power minus 8 divided by 1 minus 0.99 whole square. This comes out to be 12.57. And therefore, the flux age per relativistic norms will be equal to half raised to the power 10 divided by 12.57. Of course, here there will be 10 raised to the power minus 8 second, of course. And this comes out to be 0.6, exactly what is expected experimentally. And therefore, this experiment substantially proves the concept of time dilation. The concept of length contraction can also be understood by this. Because meson is a moving frame, and therefore the length 30 meter shall appear contracted to the moving meson. 30 centimeter will obviously appear to be contract by a factor of 30 under root 1 minus 0.99 whole square. That means 30 into 0.141, roughly 4.2 meter. And since the meson is traveling with velocity 3 into 10 raised to the power 8, almost 3 into 10 raised to the power 8, so time taken by the mesons to travel will become 4.2 into 3 into 10 raised to the power 8. You can find out T upon T half, and we will find that T upon T half is roughly 10 upon 12.57. This also supports the same observations. That means the length contraction and time dilation are the physically true concepts, and relativistically they are tested now. Their nature also supports the theory of relativity. Mesons, mu mesons are subatomic particles. They are produced by cosmic rays when they strike heavy atoms in the atmosphere. These are produced about an altitude of 6 kilometers. They have got a half-life of the order of 2 microseconds, and they travel with a very, very high speed, 0.998 c. The experiment suggests that they are found not only Earth, but they are found in deep sea, about 3 kilometers deep into the sea. See, if we observe these results classically, then the meson can travel in a half-life 2 microseconds, 2 into 10 raised to the power minus 6 into 3 into 10 raised to the power 8. That means they can travel only 600 meters before being reduced to half. Even if we take average life, we can multiply it by 1.4. Still, it is less than 1.5 kilometers. So in no case they can reach deep sea. The observations can be illustrated with the help of theory of relativity. That means either time dilation or length contraction. Obviously, to the mesons which are traveling with very high speed, the length 6 meters will appear to be contracted, and this 6 meter length will appear to be L is equal to 6 kilometer 1 minus 0.998 whole square, and this will be less than 1.1 kilometer. Therefore, not only the mesons will reach to the surface of the earth, they will penetrate deep into the sea before being decayed. Thus, length contraction and time dilation are universal concepts of theory of relativity. The same experiment can be illustrated with the help of time dilation. The half-life 2 microseconds will appear dilated to t is equal to 2 into 10 raised to the power minus 6 seconds under root 1 minus 0.998 whole square, and this will be much larger to take the mesons into the deep sea. Thank you very much.